My wife Jackie and I were supposed to be tag teaming this talk. Jackie is home with a nasty cold and decided not to infect you all, and for that you can thank her. But she sends her regards, and there's a lot of her in this talk. As Raoul said, a year ago we retired from the Johnson Space Center in Houston. Jackie as a lead for space science education, and I as curator for all of NASA's extraterrestrial samples, which is part of what this is about. We're currently living in Placitas at the north end of the Sandias, just outside of Albuquerque, and are very pleased to be members of Las Placitas Presbyterian Church. I'm a preacher's kid, and this combination of faith and science has been part of my life for as long as I can remember. And just to give you something to do besides watching the slides, I'm going to pass around a piece of another world. This is almost certainly the oldest thing you will ever handle. This piece of iron solidified about 4.5 billion years ago, when the Earth and the Sun were almost brand new. It was part of an asteroid orbiting happily between Mars and Jupiter for most of its life, and then something else ran into it, and chunks were knocked in all different directions, and some of them got into orbits that took them into the inner solar system. And this piece was part of a single chunk of iron about the size of this church that slammed into what later became northern Arizona. This is a piece from Meteor Crater. And it's exactly what you would expect a meteorite to look and feel like. It's heavy, it's got sharp edges, and I want it back. Thank you. But yeah, I'm going to talk a little bit about the science behind extraterrestrial samples, and then how space science, and particularly the studies of samples, talks to our faith and to modern scientific understanding of where and when and how we are in the universe. Is it possible to make it a little bit less bright in here without it going completely dark?
Well, not really, but we have light up front, so.
Ah, that would be good. In any case, yeah. When we talk about extraterrestrial samples, pieces of other worlds, these are very specific things. In 1969 to 1972, astronauts went to the moon and brought back soil and rock from locations across our nearest neighbor. Meteorites are, such as this one I'm passing around, are mostly pieces of the asteroid belt that have fallen to Earth and bring us samples from that part of our solar system. Also, surprisingly enough, from the Moon and Mars. There are, if you go out on a clear night, maybe even tonight, and you look up for a while, you'll see little streaks of light in the sky, shooting stars. These are in fact tiny dust-sized bits of comets and asteroids that are hitting the Earth's atmosphere at such high speed that they, in a matter of seconds, burn up. And that's that trail that you're seeing in the sky. That is pieces of other worlds completely destroyed by hitting the atmosphere at really high rates of speed. But we have samples of those, both from near the Earth and from spacecraft. And also, amazingly enough, we have samples of the sun. The solar wind is a continuous flow of charged particles from the outer surface of the sun, and a pretty amazing NASA mission a few years ago actually collected some of that material. So we really, honest to God, have individual atoms from the sun and know what that is about. And I also want to talk about our understanding of time, place, and life based on personal experience that people have had over centuries and millennia. Some of the thoughts that mythology and theology have brought to us about time, place, and life, and also some of the understandings of modern science, particularly through the eyes of these samples. So from 69 to 72, 6 successful missions landed on the moon, and the main motivation there was to beat the Russians, which we did, but a secondary and increasingly important motivation as the missions continued was to do very careful, well-designed collections of lunar rocks and soil. When we went to the moon, we had no idea what we were going to. We didn't know what the moon was, we didn't know what it was made of, we had no idea how old it was, any of those things. Analysis of the samples really told us about it. We have almost half a ton of lunar rock and soil that we curate and have sent to laboratories around the world. This is arguably the best studied material, the best studied rock samples anywhere around. And we also did a series of scientific studies of the moon, both from orbit and on the ground. This is a view that you won't see because the moon keeps the same face toward the Earth all the time, and most of that face is around that side of the moon. This is the far side. This is the view that you only can get if you're in a spacecraft circling the moon. And it actually looks different from the side that we see because there are many fewer of these dark patches that turn out to be lava flows, and a whole lot more craters made by the impacts of huge meteorites on the surface over billions of years. Come back here. Meteorites, as I said, are rocks that fall from space, and you could legitimately ask why we're introducing a meteorite section by showing people on snowmobiles. Turns out that the best place in the world to collect meteorites is in Antarctica. Partially for the very obvious reason that a black rock on the white ice shows up and you can find it. The less obvious reason is that there are some places on the continent where the movement of massive ice sheets brings that ice to a halt up against mountain ranges. The winds are so strong that the ice ablates away. It literally evaporates, leaving behind any rocks that might have happened to fall on it. And most of those rocks are from outer space. So every year, during the Antarctic summer, which we know as winter, teams are sent to specific places in Antarctica to ride snowmobiles, camp on the ice, and collect meteorites. I was fortunate enough to do this about 15 years ago, and I'm in the background there trying to get my snowmobile to work. Our team in 6 weeks collected 900 meteorites, which is pretty spectacular. And we've been doing this for decades now. And about half the meteorites that we know of in the world came from these pretty spectacular expeditions. If you want to know how to become a part of that expedition, talk to me afterwards. We can do this. I know we can do this. There we go. Most of the meteorites in our collection, come from places like this. Asteroids. Pieces of rock, little up to the size of cities, peppered by other impacts, orbiting between Mars and Jupiter. Spectacularly enough, we now know that about 1 in 1,000 of the meteorites that fall was chipped off the moon by other impacts. We know this because we've been to the moon, we know what the moon rocks and soil are like, and we can make that connection. And amazingly enough, about 1 in 1,000 meteorites comes from Mars, the little red thing up there. We know just enough about Mars to be able to make that connection based on chemistry and the way the rocks are put together. So we have free samples from the asteroids, the Moon and Mars that fall on the Earth, and we go to Antarctica to collect them. And there is a piece of Mars sitting on the ice in Antarctica. Ask me later how we know that's from Mars. We also collect bits of other worlds with airplanes. This is a very cheap sample return mission by NASA standards. When those little bits of sand-sized particles of comets and asteroids hit the Earth's atmosphere, a lot of them burn up and make shooting stars. A few of them slow down and stop in the upper atmosphere and then slowly drift down to the Earth. And it was realized some decades ago by some really smart people that if you go to high altitude and you collect the dust up there, a lot of what you're collecting comes from space. So we send aircraft, which are U-2 kind of vintage high altitude aircraft with sticky plates under the wings, and we collect dust particles, bring them back to the lab, and they turn out to be things like this, which is a fraction of a millimeter across. You couldn't see that with your naked eye, but it's a wonderful object in a microscope. This is a bit of a comet. A tiny little bit of all the dust and gas spewed out by a comet as it orbits the sun. And if we collect it just the right time, we can collect stuff from specific comets, which is a pretty spectacular thing to be able to do. Or we can send expensive spacecraft to comets, which we did about a decade ago, fly right in front of the comet as it's spewing out dust and gas, and collect that dust with almost magical material here called aerogel. This blue stuff in between the little grid bars there is a very low density material, kind of like cotton candy except made out of glass. And when tiny particles hit it going real fast, they don't get destroyed, they get caught. And this was a successful sample return mission from an asteroid, or from a comet, excuse me. There's the comet. It's about the size of a small town. It's spewing off jets of dust and gas. Here is one little particle way down there, came zipping through the aerogel, melting its way down, making this long track. But the particle is still left, and with modern techniques we can analyze it and learn what the comet was made of. Come on. We can do this. No, we can't. We're not the only ones that are in the business of collecting pieces of other worlds. The Japanese Space Agency put together a small spacecraft designed to orbit a big asteroid, touch down, and collect the dust that was on the surface. And we were fortunate enough to work with the Japanese as they brought back, again, bits of asteroid dust, smaller than a millimeter, but clearly made up of several different kinds of rock all melted together. And from this we learned what this specific asteroid was all about and how it was formed. And then there was Genesis, a spacecraft given the task of sampling the sun, but fortunately the sun spews out charged particles into the whole solar system. When that flow of charged particles from the sun hits the Earth, they cause the upper atmosphere to glow. And this is what makes the northern and southern lights. This glow that's seen near the poles is this flow of solar wind hitting our atmosphere. So Genesis was a spacecraft that had these these plates on it that were made of ultra pure materials, and the spacecraft sat out in space for about 2 years, and the solar wind atoms smashed into it and were trapped in the collector material. And the whole thing was all very fragile and very, very carefully designed and calculated, and the whole mission went superbly well until the last minute. And then bad things happened. The parachutes didn't open, and the spacecraft smashed into the ground at about 200 miles an hour. This was a bad day all the way around, but if you smash a car into a wall at 200 miles an hour, it destroys the car, but all the parts are still there. Same thing here. All the parts of the spacecraft are still there, including the collectors, which were shattered into tiny little bitsies, that's a petri dish for scale, but still had the solar wind atoms embedded in them. And through about a decade's worth of work, our folks were able to extract enough of the data that almost all of the science that the mission was designed to produce has been accomplished. So we know what the sun is made of, thanks to all those little busted up particles. Pretty cool stuff. So that's the sample set. Now how does that play with our thinking about the world and the thinking of mythology and theology? And I apologize if that meshing of mythology and theology is disturbing to folks, but they are much the same thing. And one person's mythology may be another person's theology, or vice versa. Let's think about time. Personal experience. For almost the whole history of humans on this planet, personal experience in the time dimension deals with a few human lifetimes. Yeah, I can talk with my mother. I used to be able to talk with my grandmother. I can talk with my daughter and my 3-year-old granddaughter and understand to a certain extent their realities over multi-decades. But everything else is a stretch. We can know directly about their worlds, but everything else is an extrapolation. We can guess about the deeper past. We can guess about the future. We can guess what tomorrow is going to bring. And often, because we don't know much, we assume that they are sort of like the present. And that's the personal experience time horizon. Theology and mythology are bigger. They think about the world over time scales that are generally a few hundred times or less. You can go in the Bible and see statements about how many generations it was since between the flood and the time of Jesus. And it's tens of generations. We know now that that's, we're thinking thousands of years. But certainly theology and mythology in many civilizations deals on a time scale of a few centuries. And on that time scale, human history is locally chaotic. We don't know what's going to happen for sure tomorrow. Strange, chaotic things can happen. Wars or famines or lots of stuff. But in general, slowly changing. And that's much of what mythology and theology's view is about. Major changes are rare, special, and in many cases ascribed to deities. But that's another view of the world. You know, think the Greek gods. What about modern science? What's it telling us about time? And we talk particularly, I'm coming from a geology, astronomy background, about deep time. Really, really old stuff. Geologists, 100, 200 years ago, when geology was actually trying to start being a science, said, you know, clearly things are older than a few human lifetimes. Mountains erode slowly. You can see little bits of erosion, but clearly a whole lot more has happened, implying that those mountains have been around for a long time. Fossils, bits of things that are clearly evidence of life, are there in the rocks. If you go to the top of the Sandia Mountains by Albuquerque, you can find fossils laid out that look like they came from an ancient ocean. What are they doing at an altitude of 10,000 feet? You know, some things have changed. Mostly slowly, in some cases, very rapid changes in the fossil record. That made geologists of another era think that the Earth must be much older than a few centuries. But how much older was an absolute mystery. Now we know. Astronomy and radiometric dating of rocks have given us an insight into just how old things are. Past and future events on our planet, in our solar system, our galaxy, happened on a multi-billion year time scale. That's the time scale of modern science. It's not generations, it's not centuries or millennia, it is multi-billion years. If I could sing, I would sing about how the whole universe was in a hot, dense state, and then nearly 14 billion years ago expansion started. Right? This is that time scale. This is the Big Bang. This is as far back as we can see into the history of our universe, when everything was in a very tiny condensed area, and then suddenly expansion started, and over 14 billion years we saw stars and we saw galaxies. The Earth began to cool about here, the autotrophs began to cool about here, and math, science, history is all in the very, 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 very edge of the Big Bang expansion, and it's going to keep going because the universe is expanding and it's not going to stop. So future history may just keep happening. Oops. We have samples that date back to when the sun first turned on and when the first solid materials showed up in the solar system from clouds of dust and gas. And here's one little bit of one thing. This is about 1 millimeter across. This is called a chondrule. It's a spherical bit of rock found in an ancient meteorite. And it's the kind of stuff that was the first solid material in the solar system. These are little crystals of the mineral olivine surrounded by a much more complicated shell. And this stuff solidified 4.6 billion years ago. 4.6 gigayears. The piece of the asteroid that I'm passing around is almost that old. So that's a picture of some of the first solid material in our solar system, not in our universe, but in our solar system. And shortly thereafter, about 4.5 billion years ago, the planets had formed. All those little itty-bitty bits of rock came together under mutual gravitation and cleared out the inner area around the sun, and only a few solid things remain. Those are the planets. Out beyond the planets, there's still lots of gas, lots of dust, slowly clearing out. But Earth, Moon, or Earth, Mars, the other planets, solidified in about their present size 4.5 billion years ago, and after that geology started happening. That's deep time. What about place? Personal experience up until, say, 200-300 years ago. The important scales are the distances a human can travel in a few days to a few years. Maybe dozens, hundreds, thousands of kilometers. Jesus, during his ministry, may have traveled 50 kilometers total from the place that he was born. He did make that trip into Egypt early on, but the rest of the time, and he didn't go very far. That was his world. And for most people throughout their lifetimes, they didn't go more than a few hundred kilometers, if that. They may have remained in their own village. That was the world of personal experience. And this world probably, could be understood as a closed system. A pseudoscientific term meaning no input from the outside. Certainly not affected by those little bright things in the night sky, whatever the heck they are. This world was all that there was for most of human history. This is a place where mythology and theology really expands things, partially because of those little bright things in the night sky. Smart people started noticing that they were periodic, most of them. Some of them were chaotic. And clearly stuff was happening out there. People a few hundred years ago who could predict how the seasons advanced and when was the time to plant the crops, were considered some of the most important people in the community because they understood what the night sky was trying to tell us. But essentially, there was no way to understand distances other than way out there. And theology and mythology don't talk in terms of kilometers. They do talk oftentimes about superior beings operating above, generally, up in the heavens, and generally outside of human life. But they certainly can't affect humans. Think the Greek gods, when they're playing around on Mount Olympus, every so often did terrible things to people that they didn't like. And there's a lot of this sort of thing in various myths and religions. But generally outside of human life, except, Judeo-Christian tradition is strikingly different here, in that human beings are much more closely interacting with the deity. That's a pretty rare kind of theology. Now, what does science tell us about our place? And this was one of the real revolutions starting about 1900, when people with big telescopes and some understanding of what they were looking at started putting a distance scale on the universe, stepping out, understanding that, you know, people have understood the scale of the solar system for a couple hundred years. Newton was key in that. But around the turn of the century, Edwin Hubble and other astronomers realized that things were a lot bigger than our solar system, that string of stars we called the Milky Way was actually a big, huge collection of stars, but that there were other things just like the Milky Way out there at greater and greater distances, and stepping that distance scale out to our present understanding of the universe has been one of the great triumphs of modern astronomy. We now understand that our planet, our solar system, and even our galaxy are only single and unexceptional examples in a universe tens of billions of light years across. A light year is billions of kilometers, so you're multiplying billions times billions, and that we are just a tiny, tiny speck in a monstrous, monstrous universe. And we're not a closed system, even though we'd like to think so. Our planet and our solar system are, in fact, affected by material from even further away. Come back here. Okay. Locally, for instance, comets and meteorites that deliver little dust grains like this, that little dust grain has almost 20% water in it. And this stuff has been bombarding the Earth for 4.5 billion years. Comets and meteorites delivered a significant fraction of the water in the Earth's oceans. Maybe half, maybe even more, coming from outer space. That is not a closed system. In the early solar system, there were a lot more planet-sized things orbiting around, some of them in fairly chaotic orbits. And as might be expected over a long period of time, some of them collided. An object about the size of the small planet Mars, for a little less than 4.5 billion years ago, almost certainly collided with the Earth. You can imagine what a wreckage that would produce. The smaller object was mostly incorporated into a still partially molten Earth, stirred around. You can't find part of it anymore. You can't find the whole. The thing that we do find is the collisional debris that was thrown off Earth but into Earth orbit. That coalesced in a very short time under mutual gravity to form the moon. That's what the moon is. It is the rubble from a collision between two planets early in the history of the solar system. It has since melted, overturned, lots of things have happened to it, but all the stuff that makes up the moon is in fact debris from a collision between the Earth and a somewhat smaller planet. That again is an idea that is decades old but no older. Getting the samples back from the moon really helped us to nail this one down, and people are still trying to understand exactly how it worked, but that is almost certainly what the history of the moon is. Going to the moon, one of the surprising things coming out of the samples, this is a single moon rock from the Apollo 16 mission, made up of chunks of lots of different rocks, smashed, heated, melted together. showed us that the way you make a rock like this is by pummeling the surface with multiple impacts of other big asteroids. And these are all over the moon. This is some of the most common rock on the moon. It would be one of the most common rocks on the Earth if we didn't have an atmosphere that was stopping a lot of these big meteorites from smashing into us. And all through the solar system we find the same sort of stuff. Impacts over billions of years are the major geologic agent making the moon and planets like they are. And finally, one of the really neat things that we found from samples and really microscopic bits of them, like this little bit of 1 grain of comet material, this is a fraction of a millimeter across, this little bright thing. We can analyze that, we can measure its chemistry, and we can measure its isotope composition, and there is nothing with this kind of composition anywhere in the solar system that's made here locally. This particular composition was made in an exploding star someplace out there. We don't know where, we don't know when, but early in the history of the solar system, another star in the Milky Way exploded, and it blasted tiny bits of very strange composition, solid material, into the gas cloud that was becoming our planets. And there's a little bit of it. That little thing may be 10 billion years old, better than half the time since back to the Big Bang. It came from an exploding star that was not the sun, and we have it in our laboratories now. That's cool. If you're a particular bent, you think that's cool. Let's talk a little bit about life. Everybody likes to talk about life. Personal experience suggests that humans are unique, dominant, and everlasting, and that my type of human is clearly superior to that other type of human over there. That's what personal experience says. We share the world with a few hundred types of animals that we watch, use, kill, or eat, and not much else. That's life from personal experience, and there is no evidence whatsoever of life out there unless you're from Roswell. That's a different story. Mythology and theology often posit beings out there with special powers and abilities. That's what mythology and theology are about. Animals. Maybe they're fated to be our servants and our food. Genesis says Adam and Eve would have dominion over all the animals. They could use them as they like and even give them names. In other theologies, they may be equally important to humans. Every bit of life on Earth is unique, sacred, and special. Or in some cases, some of those animals may be gods. Lots of different treatments of animals. In some theologies, humans are centrally important, Judeo-Christianity. In some theologies, not so much. Aztec mythology, virgins regularly sacrificed. This is not centrally important. What is science telling us about life? Just a couple of ideas from modern life science that I find particularly spectacular. How about this one? All life on Earth is related. In chemistry, all life uses the same set of chemical reactions, and if you go into the DNA of any living thing, any species, you'll find enough overlap to understand that all life on Earth is intimately related and essentially the same thing. That we had common living ancestors that evolved to form all of the variety of life that we see on Earth. Life existed almost as early as conditions would allow. The early Earth was really hot, For a time it was molten, it cooled down, water came in about the time that the Earth got cool enough that the oceans weren't still boiling, i.e. when the conditions would allow some kinds of life, we find chemical and then later fossil evidence of at least microbial life. So basically, as soon as life could exist on Earth, it got started. And then it evolved and got complex. Right now, there are not just a few hundred species of animals, what we can see. The estimate now is there's about 10 million species of life. Most of them microscopic, most of them single-celled, but different. But that's a whole different number than a couple of hundred. And over 99% of all the species that ever lived have gone extinct. That's a discouraging thought, but it is in fact true. That there are things that happen in the Earth's environment that kill off not only individuals, but entire species. And most of them are gone. And what's left is the ones that have survived. And then there are a few things that we understand specifically from space science and samples. Habitable environments, places where the chemistry, the temperature, the physics are benign enough that things can live, exist or have existed certainly on Mars, and likely on at least two other places in the solar system, Europa, the moon of Jupiter, and Enceladus, the moon of Saturn, where we see water, where the chemistry and the temperature are okay. Complex organic chemicals, even up to the level of amino acids, and extraterrestrial life, if it exists, can be transported between planets without sterilizing conditions, and I'll show you that in a minute. And mass extinction events, some associated with meteorite impacts, have nearly destroyed all life on Earth many times over. And then life comes rebounding back. And when this happens, it opens up new ecological niches for the survivors. And we'll see that in a minute. Here is a thin slice, maybe a couple of centimeters across, of the oldest meteorite that we have from Mars, over 4 billion years ago. Old. The white stuff and the orange stuff are minerals that were formed when water moved through this rock at fairly low temperature. This rock provided a habitable environment 4 billion years ago on Mars. Our spacecraft have now found places much more recent than that, where water has flowed, the chemistry is right, the temperatures are reasonable. There are places where if life existed, it could have persisted. This is a fairly famous meteorite that fell in Mexico in 1969 called Allende. It's a carbonaceous chondrite. It is the oldest, most primitive type of meteorite that we know of. It contains complex organic compounds up to and including amino acids, the building blocks of DNA, that were formed not by life processes, but by physical processes out in deep space. But these things have been raining down on Earth for billions of years and may well have contributed a significant amount of the organic chemistry that makes up all of life. There's that meteorite from Mars again. It is essentially the same as it was when it was sitting on Mars as part of a lava flow. It was not remelted in the impact that threw it into space. It wasn't heated past the boiling point, either going into space or coming screaming through the atmosphere. If there had been a little microbe living in there, coming from Mars, nothing in the subsequent history of that rock would have destroyed that microbe. Basically, impacts can move rocks between the planets without either melting or sterilization. If life got started on Mars, it could have ended up here. And then there's this story, which everyone has seen, This is the impact 65 or 66 million years ago of a huge meteorite over what's now the Yucatan Peninsula that happened exactly the same time within error bars that are now just 11,000 years of the most recent mass extinction that killed off a huge percentage of the species on Earth, including our friends the dinosaurs. The dinosaurs had reigned supreme for 250 million years before this happened. This happened 65 million years ago. If the meteorite had not come in, there is little reason to think that the dinosaurs wouldn't still be around as the top dog predators on the Earth. Our ancestors, the mammals, were little things about the size of a small rat, running around, hiding in holes, trying to avoid being dinosaur snacks. If the dinosaurs hadn't gotten wiped out, that's what the situation would still be. But when the top dog predators get knocked off suddenly, this is good for the little guys. They can come out of the holes and start to evolve. Good for us. We are here as top dog predators because of that. Finally, it said that in normal human experience, there's no evidence of any life out there. Right now, on this very date in 2016, science has yet found, or certainly has yet to publish, any evidence, any clear evidence of life out there. But that is subject to change at any time. Within the last few decades, for the first time in human history, the search for extraterrestrial life is being conducted as a legitimate scientific search rather than being the place of theology or mythology. And there's basically four kinds of searches going. Searches of meteorites and other extraterrestrial samples for possible evidence of life. In 1969, colleagues at Stanford and NASA published that picture, which might be a very tiny microfossil of a single-celled organism. Most scientists don't believe that, but that was in a meteorite from Mars. Most scientists currently don't believe the case has been made, and the search continues. We're sending spacecraft to places in the solar system where life might be found. Europa, the ice-covered moon of Jupiter that almost certainly has an ocean underneath, is a place we're going to be exploring probably in the next decade or so, looking for evidence either on the surface or below the ice for the existence of life. With the advent of telescopes that can show us planets around distant stars, we are on the verge of being able to make measurements of the compositions of atmospheres and planets around other stars. The composition of Earth's atmosphere is a definitive sign that there is life here, specifically life that does photosynthesis and makes oxygen. The combination of elements and compounds in the terrestrial atmosphere is an absolute biosignature showing that there's photosynthesis going on here. If we found that same mix in the atmosphere of a planet around another star, that would convince a large part of the science community that we were looking at another place where life existed and was affecting things on a planetary scale. And finally, we are continuing to listen for evidence of interplanetary communication, not using the VLA, as Jodie Foster did, but using other radio telescopes listening to star after star after star at frequencies, trying to hear if there are other technological civilizations out there who are broadcasting and we're picking up their signals. That search is going on now. So we got 4 different kinds of scientific searches. We don't know if or when any one of them will hit. But as we found this last week, after decades of searching for gravitational waves, they were finally heard on 2 very sensitive detectors. Some of our detectors may well find one of these. I am reasonably confident in my lifetime. I am highly confident within my granddaughter's lifetime that we will have evidence of life somewhere else, either in our solar system or in our galaxy. So just a couple of wrap-up thoughts for discussion. Personal experience of time, place, and life is extremely limiting from what we know now, but is sufficient and has been sufficient for most people for most of human history. You don't need religion, you don't need science, you just need personal experience to understand what's going on around. Mythology and theology, in almost all cases, expands our view of time, place, and life, but it often requires faith in things unseen. And that works for some people, and it doesn't work for others. And modern science in the last 100 years has immensely expanded our understanding of how old things are, how big things are, and how complicated life is. But these scales are often unseen and, for many folks, almost unimaginable. That's the story. I would be happy to play with some questions or open this up to discussion. Thank you very much.
There'll be a period of 5 or 10 minutes for questions for our speaker. We'll be departing from our usual practice of having a separate discussion after refreshments because our speaker needs to. He's got an early flight.
Catch an early flight, and,
We're gonna have
and some folks have long drives. I thank you for being here. Are there questions or discussions? Yes, sir.
What is the process of dating something?
What is the process of dating something? It's based on the fact that there are radioactive elements in many materials that change at a very known rate. Radioactive atoms split into other kinds of atoms at a rate that is precisely known. So if you have a good idea of the composition of your starting material, and then you measure what you have in an older sample and see those decay products, the stuff that the atoms split into, you can turn that into a clock that actually gives you a date since the rock became a closed system, since the rock solidified. That's what you're dating. You're measuring radioactive materials and turning that into years. Carbon-14 dating is the best known of these. It has a useful range of a few thousand years. It tells us lots about archaeological samples. How long since a tree died, for instance. We can measure that very precisely. For dating rocks, we use other kinds of radioactive atoms, potassium, uranium, thorium, that decay much more slowly. Other thing, yes?
When you were saying that the scientific community at this point does not feel that they have discovered life anywhere else, and one of the ways that you're detecting that is checking out these atmospheres. But you're pretty much using our carbon model as the basis of life, what's to say that there can't be another life form that isn't the same as ours?
There is nothing to say that our life form is unique. At one level, if we found a planetary atmosphere that was very rich in oxygen, that would be a smoking gun for something like photosynthesis. But if we found a planetary atmosphere where things were out of equilibrium, where there were several different kinds of elements or chemical compounds that we know would react with each other and go away very fast, finding this disequilibrium is a pretty good sign that something active is happening. And scientists would immediately be going into that particular atmospheric chemistry to try to understand whether this is telling us about volcanoes or whether it's telling us about life. We have this example right now. We've detected methane, a natural gas in the atmosphere of Mars. It should decay away in about 300 years. The fact that we see it either tells us that there are living things producing methane in the soil of Mars, or that there are volcanic processes going on that are continually venting it, and we don't know the difference. If we found similar things in the atmospheres of other stars, we would argue hard about it, and we would never be able to go there and field check it. But you may well hear within the next few years about exactly this, because we're just now at the point where the observations are good enough to make these measurements. Other question? Yes, sir.
I take it that there's no way that water can be formed naturally in our environment here on this planet. And therefore all
Right.
water must
Okay.
have come from...
Yeah, you make water by having oxygen and hydrogen and basically combining them with either by burning or by sparks or something like that. There's so much oxygen in our atmosphere that any free hydrogen gas is immediately burned up and converted to water. So in an oxygen-rich atmosphere, world like ours, we're not producing water now, nor were we in the past. Water either came up from the ground through volcanoes, or it came from space.
Now, excuse me, how about oxygen? How did oxygen get here?
Life.
Without photosynthesis?
Every rock is made up of minerals that are about 50% oxygen, but they're all bound up in rocks. Early single-celled organisms, we used to call them blue-green algae, learned the trick of taking dissolved rock minerals and breaking apart the bonds and releasing oxygen using sunlight for the energy source. It's called photosynthesis. Earth has an oxygen atmosphere because of the rise of single-cell organisms that knew how to do photosynthesis, and this happened at about 3 billion years ago. We can see it in the rock record. Before that, there was no free oxygen on Earth. So the fact that we have an abundance of oxygen in our atmosphere is an absolute sign of life here. Yes, sir.
That interstellar sample that you showed, had a couple questions about that. The mineralogy, is it's unique mineral? And also,
it's,
were you able to isotopically age it?
Okay, the minerals are fairly unique. The mix of isotopes was absolutely unique. There are instruments now called secondary ion mass spectrometers that can bombard micron size areas on a sample with enough energy that we get signals not only from the different elements, but from the isotopes of those elements. And we can compare that to other minerals on Earth and also to what we see in the spectra of supernova and red giants. The ability to do this is maybe 2 decades old, to look at microscopic spots and do isotopic analysis. But that's where that came from, and it ties microscopic science to astronomical observations in just a beautiful way. Other questions?
Any questions?
Thank you very much.
Thank you.
Who's got my rock?
Who's got my rock?
You got that.
Thank you.
We have lots of refreshments left over. Please help yourself or take some with you if you'd like.
We may just have
Thank
to
you for
try
coming.
it. We may have to try it.
I didn't kick it once.
Because